Right. So we are continuing our discussion about clustering by talking about density-based clustering. And this is going to be the last clustering method we are going to talk about in this class. As usual, we have the idea in mind how to split the data set into pieces, right? So we are always after some kind of grouping of your existing data. And we always came up with certain criteria which would end up some kind of meaningful groups of our data points. So it has been the practice for a while. And for k-means, k-medoid, hierarchical clustering, we adapted several things, and we have some underlying hypotheses, underlying axioms, and other stuff. And now we are going to talk about something a little bit different than the earlier approaches. Okay, so the idea here is the clusters are kind of dense regions in our data space, and we are going to separate them by regions of lower object density. So we are not really looking for something really like a spherical or something really smooth. It can be any shape, basically. All right. So in the earlier examples, if it were like a hierarchical clustering, we were looking for some kind of hierarchical nature of the clustering, and it was the idea how we can actually build a cluster step by step, starting from individual points. On the other hand, in the k-means, we had those stuff, we had data points, and suppose you were looking for a two-cluster representation of your data, and we were after some kind of grouping like this, another grouping like this, but we didn't really pay attention to the fact that maybe we could have had something like going in this direction like this, all right? So we kind of forced earlier to split the data into, let's say, two regions, which would represent some kind of circular representation of a group, and there's another circular representation of another group, and there used to be a centroid here, there used to be a centroid over here, and if you just look at these two pictures, you see some kind of, at least some kind of structure, some kind of ordering of your data. It is kind of organized in a certain way because of the assumptions that you made at the beginning of this process. Okay, so now, however, we are going to dive into another territory. In this case, we are looking for more about densities rather than some kind of centroids or some kind of hierarchies. We are basically motivated by density of our data set. If we happen to see anything connected based on some kind of density like this and like that, that means we can claim those to be some clusters. So you see they look more like a bacteria, right? They are not really some kind of a circular area, or maybe you don't really claim any kind of hierarchy between the clusters and so on. That means we are really shooting for something else. Okay, so idea is basically you are looking for connected points based on and they are going to be connected, they are going to be a density based the connectedness will be defined based on the density, and if they are connected through some kind of criteria that we are going to define very short, and then we are going to claim that, hey, this group, and when you reach the maximum level, maximum boundaries, maximum number of points, and you cannot really move beyond these boundaries based on that criteria, we are going to claim that, hey, this is the cluster, and we are going to stop there. So we basically discover one cluster, and then we are going to check other data points in our data set and to find out whether they are connected to anything else in the data space. If you look at the red cluster, suppose we have these data points and looks like they are close to each other, you know, there's some kind of criteria going on, which I'm going to define later. One more time I'm saying this, right? So basically they are all connected to each other based on some kind of proximity and density. And these are like the boundaries of this region of this cluster. Similarly, for the blue cluster here, I have the boundaries here, and what I observe here is that I cannot really move from the boundaries to another cluster, and I cannot really expand this just because there is a reason for that. Okay, so it looks like this is the maximal set, this is the maximal area of interest I can grow up to based on the densely connected data points in my data space. This will basically, hopefully, and usually will lead to some clusters which will be in arbitrary shapes. Okay, and this method actually implemented by the DBScan algorithm, and there are of course versions of this algorithm too, but the initial idea is going to be density-based clustering algorithm. Okay, so let's move on. So main features of this kind of algorithm is this kind of clustering methods is that, again, they are able to discover clusters of arbitrary shape, and they can handle the noise. So if you recall your k-means, this data point over here somehow, I mean, would shift the cluster to that direction, let's say. But in this case, maybe just because of this density criterion or density criteria that we are going to introduce, maybe we are going to end up and say, hey, this might be an outlier, and this might be a region which is densely connected. And I'm going to end up saying that this is my cluster. Okay. And I'm going to be able to handle this data point. And maybe I'm going to declare this without any given parameter like k. I'm not going to say anything like, okay, I need 5 clusters or 3 clusters or 5 clusters. There is no such restriction here, so I don't have to really know how many clusters I'm going to end up with. All right. So it's kind of natural process. It is going to discover number of clusters by itself. However, I'm going to provide some kind of parameters. So those are going to be needed to be able to end up my algorithm, right? So it's going to help me stop the algorithm. And this complexity-wise, it is a really nice one because it just requires one scan of your data, and then once you got the distances, and you'll be fine. Okay, so it will lead you to densities that you are going to discover. So there are several versions. I mean, there are actually improvements. There are some kind of new ideas on top of this. But we are going to basically talk about the DBScan algorithm in this class. If you have any interest on the others, you may want to check the other resources and the book as well to find out how the other algorithms actually differ from our original algorithm. Okay, and there is also an implementation of this algorithm, which is called SCAN. Actually, it was published, I believe, in 2007 or 2008, and this idea was implemented to networks. You know, in the social networks, you have links, right? And you may want to discover whether these people are forming a cluster or not. So I did this in my research too. So I was really looking for social networks and clusters and group of people who basically form a group together, a cluster together. So it was part of my research. So that's why I'm kind of interested in this. And yeah, of course, the same person here, Dr. Shu, and he's the original. He's one of the author of the original algorithm, and he expanded idea to SCAN algorithm, which is specifically targeting for network clustering. Okay. So we are going to need 2 parameters to discover those clusters. The first parameter I'm going to introduce is called epsilon. It is nothing but the radius of my neighborhood. Okay. If you recall my earlier, if you go back and check or remember the earlier representations when we talk about KNN, I hope you remember KNN algorithm, right? It is K nearest neighbor algorithm. At that time, we were looking for a number of points around us for a given point. But at the same time, I mentioned that for a given point, you may want to also investigate a neighborhood for this individual data point. Suppose you have a point P, and you may want to go this direction, that direction, that direction, and this direction. You draw a circle around your point, and that radius is called epsilon. Okay, so we are gonna refer to this guy. That is nothing but a distance. All right, and you can define the distance, the metric for the distance by yourselves. It shouldn't be a big issue. It is just the distance. It is how far you wanna expand your neighborhood. Okay, if you wanna really look beyond this point, you may wanna basically increase your radius, and you can just increase your epsilon if you wanna really increase the size of your neighborhood. Okay, so that is one thing you have to consider. Second thing is the minimum number of points. We are going to denote this with win PTS, which basically refers to minimum number of points in the epsilon neighborhood of your point. Suppose again you are a point here, and this is your neighborhood, and suppose these are all data points that fall under that fall in your neighborhood, and we are going to say, well, you have to have at least 3 points in your neighborhood, for instance. And there will be a reason for that, okay? So for the time being, don't worry about it, and we are going to explain this in a second, okay? Suppose we have data points, and suppose you choose a point over here, and you say, okay, this is my epsilon neighborhood, and you just count how many data points that you have in your neighborhood. In this case, you have like 5 of them. Suppose your minimum number of points is 3. If that is the case, that means you have more than enough, okay? You have more than enough, and that will lead you another thing, okay? So we are gonna exploit this idea when we talk about the process of clustering, okay? So let me, yeah, sorry, I had to pause the video recording for some reason. So let's give a definition for the neighborhood. Okay, so I kind of try to draw a picture for this and to illustrate what a neighborhood looks like, but let's try to give a formal definition of this. Suppose you have a P, all right? And what you're saying is that based on such an epsilon, you want to define a set which is called N. That means you are going to have a bunch of Qs. They belong to the same data set, but there is something in common with this Q, right? So not every Q actually will be a member of this set N. So those are the Qs such that the distance between those Qs and me as a P, as a point, is going to be less than or equal to my epsilon that I set, okay? So if you recall the earlier picture one more time, so suppose this is your P, and you are saying that, hey, I'm going to give a distance epsilon, which is my radius, and I'm going to draw a circle around me. And whatever the Q points, Q1, Q2, Q3, let's say Q4, and they'll be forming my set N. Okay, they are going to be all part of this an element of this neighborhood. So this is nothing but a set, by the way. And you can also represent this like NP, N epsilon P. So this is nothing but a set in which maybe in this case you have Q1, Q2, Q3, and Q4. Just an example, okay? I hope this is clear right now. So you basically have neighbors, and this is your neighborhood. You think about yourself like you are living in a street, you have a house, you have an apartment, whatever. So in your vicinity, you call these people your neighbors based on some distance, okay? So in my culture, for instance, we basically count anyone who is like 40 blocks away, I believe. No, maybe there used to be a distance, okay? So who you could call a neighbor, all right? So you basically define your maybe like 40, not blocks, it is just basically 40 houses or apartments away from you are all considered your neighbor, okay? It's a cultural, basically criterion set in my culture. So we basically have the same thing going on here. Okay, so there is another important definition I would like to share, and this is maybe the fundamental of fundamentals. So these are fundamentals of the clustering method. Okay, so that's why we have to go through these definitions. So the first thing I'm going to talk about is directly density reachable. So in this case, you are going to have a point, all right, and what you're going to say that, hey, this point P is directly reachable, density reachable from another point. Let's call this Q. But this reachability is defined based on the earlier parameters we introduce. So there's an epsilon, and there is also these minimum points, okay? So based on this, you are gonna call, or you are gonna say, you are gonna make a claim such that your P is directly density reachable from another point Q. Okay, so let's try to explain this in more detail. So first of all, your P has to be in your neighborhood, right? If you are the Q, the point in the center. Let me adjust this example based on this so that you don't mix up the terms. Okay, yeah, this is basically so in the previous one, in this one, the point I was looking was P. In this one, the point in the center is Q. So I'm gonna just draw the picture one more time. So don't worry about it. These are just Q's and P's. Looks like there is a Q here. There are P. There's another P over here. Okay, and suppose you have other points here, and the point which is your point of interest is Q in this case. And what you are saying is that, hey, the P first should be a part of my neighborhood based on an epsilon. Okay, looks like I have an epsilon, radius is epsilon, and P is within the boundaries. Okay, so far so good. And the second condition is that this size of this neighborhood that belongs to Q should have at least minimum number of points. If you say minimum number of points is 3, that means for this guy should have 1, 2, 3, at least 3 points. And of course, P should be one of them, all right? Looks like in this case, I have, again, 5 points. It is already satisfying this condition because the size is 5 and minimum number of points is 3. Looks like this is also okay for this guy. So you see what happened? What we discovered is that P is directly density reachable from Q with respect to what? With respect to epsilon and minimum number of points. This also necessitates that this point Q should be a core point. Okay, looks like we have a new definition. What is a core point? A core point is a point which has at least minimum number of points in its neighborhood. Okay, so that's the definition. If you have enough number of data points in your neighborhood based on epsilon, if you satisfy that condition, that means you are a core point. One more time. Q must be a core point, and P must be in the neighborhood of this Q, and then you can say that P is directly density reachable from Q. Okay, that is the definition of directly density reachable. Okay, in this example, we have Q here, and the neighborhood looks like it is 1 centimeter. And in this vicinity, I have a circle, which is the boundaries, right? I just count how many points I have. 1, 2, 3, 4, 5, 6, 7, 8, 9. If you consider this, maybe you can also say 10, all right? So it looks like at least 9 points around you. That means the size of the neighborhood is already what? 10, which is already greater than 5. That means this Q is a core point. And at the same time, P is a member of this neighborhood. That means this P is directly reachable, density reachable from whom? Q. That's the conclusion. Okay, you may ask, I mean, why and where and how are we gonna need this? Just be patient, okay? We are gonna see other definitions and you are gonna find out why this is something very important. Here, what we are trying to discover is that basically, which points are really connected to each other so that I can expand my cluster based on this vicinity, okay? This proximity and closeness. Okay, let's move forward. So one more time, the definitions: a point is a core point if it has more than a specified number of points. So the criterion is basically you have to have at least minimum number of points in your vicinity, in your neighborhood, with respect to an epsilon value. And these are basically interior. If you happen to have a cluster, let's say a circle like this or like this, all right, these are going to be located at the center of your cluster. A border point has fewer than minimum number of points within epsilon. So, but it is in the neighborhood of a core point. Looks like if you have a point which is directly reachable from a core point, you can call this guy a border point. Okay, but you don't worry about this too much. Okay, it's just a definition. We are not going to really exploit this a lot. We are going to be more interested in core point. And noise point is, I mean, it is kind of self-explanatory. I get it is more like an isolated one, and it's any point that is not a core nor a border point. That means what? It doesn't have enough neighborhood to become a core. At the same time, this guy is not directly reachable from any other core data points. So it is kind of isolated, far away from the connected data points. It is far away from the existing data space. So this is, again, something really important to remember. Okay, let's move forward. Now let's try to build our new definition based on the earlier definition. What was the earlier definition? The earlier definition was directly density reachable. But be careful, now I'm talking about something called density reachable. Looks like you got the idea. Okay, I can feel that. All right. So the idea here is that, well, your point, any point that you pick, looks like doesn't have to be a direct neighbor of your core point P. Rather, it can be any other point which you can just trace several points and reach and hit that point later on in the time, okay, in the space. So let's move on and give a definition for this. So a point P is densely reachable from a point Q. Again, I have a Q point, which is a Q, which is a core point basically. And then I have a P point P, and what I claim is that P is densely reachable. It is not directly densely reachable just because it is not in the neighborhood of this Q, but what I observe is that there is a path. If I follow this path, I can reach this P, but how? So let's follow the rest of the definition. So it looks like we have a Q. Again, every time we have to consider epsilon and minimum number of points. If there is such a chain, let's call this chain P1 and through Pn, where your P1 is Q and Pn is P. Looks like you are going to start at Q and you are going to end up with whom? P itself, who is represented by Pn. And the condition is that every Pi plus 1 is directly densely reachable from a previous data point, which is denoted by Pi. Okay, I hope it is starting to make sense, right? It starts making sense. So what happens here is that if the number of points, the minimum number of points is 7, and if you, I think this is not supposed to be, there is something wrong with this diagram, I guess. Okay, I try to fix it, but I think again, it's shifted a little bit in the presentation. Different versions of Office I'm using, so it's kind of distorted, I guess. So suppose this guy is a core. Okay, let's count the neighbors. 3 here, 3 here, and 1 here. Looks like this is a core, right? Because it has at least 7 members in the neighborhood, and this neighborhood should have been shifted a little bit towards this direction anyways. So in that case, what you are saying is that it is really distorted. So, okay, let me try to, fix this a little bit. So let me clean this one. So this P was supposed to be a member of this circle, okay? I hope you got the idea. So this P1 should be in the neighborhood of this because it has to be directly reachable, right? And after this point, what I observe is that, let me change the color for you guys. Let me make this green. So look at this P1 that I had just reached. So I draw a circle around it. Why do I draw a circle? Because I talk about epsilon neighborhood, which is the radius of my circle that I'm drawing, an imaginary circle that I draw around myself, okay? So P2 is reachable, but directly reachable and directly density reachable from what? This P1. Once I get to P2 and I draw another circle, let's say, and change the color a little bit, make this red. So I'm gonna draw another circle around this guy, and my P2 is here, okay? And my P1, let me delete this one. My P1 is here, okay? And looks like my neighborhood actually includes this guy, okay? Yeah, shape was not really correct. So I just tried to illustrate this by drawing over the lines, okay? So basically we can redraw the things one more time. Suppose you have one P1, so you have another P2 here, okay? It is not really proportional. Let me, suppose you have a P2 here, which is your direct neighbor, right? So I'm gonna draw another circle around this guy. Gosh, my circles are not really good. And let's say you have a P3 here. I draw another circle around this guy. Suppose I have a P4 here, and I draw another circle around this guy. It looks like I have my final P is over here. You see, every step, P2 is, like say, every PI plus 1 is a directly reachable neighbor of PI, so that I can basically travel around this direction and reach my final P, which will conclude that P is density reachable from Q. Again, you can ask the same question, why is it that useful? And we can answer as follows. Once you find a path like this, that means at the end of the day, they are going to be part of the same cluster because they are all densely connected. Okay, they are all connected at the end of the day. So we are actually trying to understand the fundamentals of this approach. Okay, so and finally you can conclude that P is, and all of them form, they are going to all form a chain, and at the end of the day you are going to reach your final destination. Okay, I hope it is clear now. And now reachability is passed, and now we are going to talk about something else, which is called density connected. And this is the last definition. Okay, this is the last thing I'm going to talk about to describe the neighborhoods and the reachability and so on. Okay, so suppose you have points P, you have also point Q. Okay, so the claim is that a point P is densely connected to a point Q. Okay, with respect to epsilon and minimum points, as usual, these are my bodies, right? So epsilon and min points, always keep that in mind. These are gonna be always there, okay? If there's a point O such that, so there's a point in a way that P is P is densely reachable from O, and at the same time, Q is also directly reachable from O. If you recall, directly reachable, densely reachable. So your first degree neighbor is always your directly densely reachable. But if you have to travel along several points and reach to a guy who is in your maybe 3 hops away neighborhood, then you call it like density reachable, not directly density reachable. So in this case, in this picture, P is density reachable, and Q is also density reachable. Okay. Okay, so what's the conclusion of this? The conclusion here is that your P and Q may not be densely reachable from each other. Okay, so probably, let's say your P doesn't have enough neighbors. Suppose you have a P here, it has only one neighbor here. So you cannot really call P as a what? A core, but you may have another point. You may have another point here. From here to there, okay, you can say, hey, you are my border point. Let's say there is a O here, and there is a P. You can say, hey, P is in the neighborhood of O, and P is directly reachable from O. That's correct. And O is a core point, but P is not a core point. Suppose your condition to be a core point is to have at least 5 points around you. Okay, so P has only 2 points. So P cannot be a core, but it can be directly reachable from something called O. Okay, or it can be densely reachable from something called O, like this. You see? And similarly, you can have a Q here sitting in another neighborhood. It has only one neighbor, let's say, but there might be another point, something like this, and there is a guy over here. Okay, and this guy might be a point. Let's call this guy T. T is a core point, and Q is only directly reachable from whom? T. And here we have a similar story. Q is densely reachable from O, but you cannot really make a conclusion, okay, Q, because Q and P are not core points. You cannot start and draw any kind of reachability conclusion from either points. You cannot do that, okay? So the only choice you are left with is to find out someone in the middle from which you can be reached, okay? And by the help of this one, you will be connected, like in this case, okay? So we are gonna call this concept density connectedness, all right? But you are not really you are not reachable. You are not reachable in any ways. You are not directly reachable. You are not density reachable. You are just density connected. P and Q I'm talking about. Okay. I hope it is clear now. Again, I'm going to use this concept when I want to merge my clusters. Okay, when I want to merge my data points so that I can get bigger clusters. Okay, let's continue with the discussion on DBScan, and we are gonna give the algorithm shortly in next slide. Okay, so again, relies on density-based notion of cluster, and the definition for the cluster is that it is the maximal set of density connected points. I hope it makes sense now. It makes more sense now, I hope. Okay, so you are gonna try to see how much you can extend and extend and extend, and finally you cannot make a jump from this point to this point because they are not densely connected. Okay, that means you may have to create another cluster just because you guys are separated from each other based on epsilon and minimum points. Okay, again, every decision I'm gonna make, it will be based on these two parameters. That is some kind of disadvantage of this method, but it is not really a big disadvantage. Okay, you can call it like caveat of this algorithm. Okay, and it's gonna help us discover arbitrary shapes as a cluster. Okay, the algorithm is as follows. You are gonna select a point, just random, and then you are going to retrieve all points which are densely reachable from your P, again with respect to your epsilon and minimum points. Okay, so you are going to decide if P is a core point. Okay, if P is a core point, then you are going to declare a cluster around this P. Okay, and then you are going to keep checking other points. If your P is a border point, however. Looks like it might be a member of a neighborhood. And no points are densely reachable from P. In that case, your DB scan is going to visit next point in the database because you cannot start a cluster from a border point. Okay, so a border point can be a member of a cluster. All right, suppose it's a core. Suppose maybe it should be same size because we have the same epsilon, right? I lost the earlier one. Funny. Okay. So let me put several points here so that it will be clear that this guy is clearly a core point. Suppose I have these 2 points here. Again, this is not a, maybe I should have drawn the point over here. Okay. Suppose you have minimum number of points is 3. Yeah, this is a core, but this cannot be a core because you have only 2 points in your neighborhood. And on the other hand, maybe not on the other hand, maybe in addition, this point is a member of this neighborhood. Let's call this P. Let's call this Q. Q is a member of this neighborhood. Q is an element of what? Epsilon neighborhood of whom? P. That means it is a border point, but not a core because it doesn't satisfy the condition for the minimum number of points. Let's say it is 5. Okay, you have only 2, so you cannot really satisfy the condition. In that case, this guy cannot initiate a cluster, but as being a member of another neighborhood, it can be a part of this cluster once you discover one cluster over here. Suppose you skip this guy, and in your next iteration, you happen to see P. Well, all the guys over here will be part of this cluster as well as your Q. Okay, so you see Q is joining another cluster, but it cannot lead a cluster. It can be a follower, but it cannot be a leader of a cluster. There's a distinction here, okay? Just keep that in mind. So we are going to do this over and over and over and over until you process all the points. So you have to really make sure that you either merge a point to a cluster or you visited a cluster. Once you have these points, once you declare a cluster over here, once you assign all these points to this cluster, you don't have to check them one more time. You are done with these points, okay? So while you are going through the data points, as soon as you assign them to a cluster, you don't have to see them again. So you can just skip those points, mark them checked, and you can move to the next one. Okay, other points. All right, let's move on. So we are going to have our epsilon. Suppose in this case we have 2 centimeters, and let's say minimum number of points is 3. So what I'm going to do is I'm going to start. Suppose this is my data space. I'm going to start from somewhere here. Okay. Looks like I started with a point, and it is a core point just because minimum number of points is what? 3. So I can just declare, hey, you can be a cluster, and from there I can try to see who is densely connected to me. And I just keep traveling around, and I discovered that this guy is also a member of this group. So I can merge it to that group, and I can assign, I can say that, hey, you are going to be a cluster. So I found my first cluster. Okay, yeah, visually I can see there are 3 clusters, but let's see the process. Okay, so suppose I declared them earlier and they are still there. And then next point, you see I'm not going to check the other points because they are already member of this first cluster, C1. And now I'm going to visit the next point in the data set. Well, check the neighborhood. Does it satisfy this condition? No. Then it is a noise, basically. I just say, hey, I can call you a cluster, but there will be only a single member of this cluster. And then next is going to be the third group of points. And I'm going to, oopsie, probably you are going to see whatever the points, yeah, there are several things really embedded here. So you may want to just start this point. Okay, let's start this point. All right. So let's check the neighborhood of this point. Okay, these are all part of this guy, and there is no other point there, so I don't have to really worry about that. And this is gonna be my third cluster. One cluster, second cluster with only one single member, and this is my third cluster. Okay. Parameters are important, and if you play with the parameters, things are gonna change. Okay, because it will tell you how are you going to decide whether something is going to be a core point, a border point, or a noise. Okay, so that's going to be the core concept here because it is related to your core. Okay, so suppose in these examples, we fix number of points to 4, but we just lower the epsilon value. Okay, so what you do here is that you keep the epsilon like bigger. Suppose your epsilon is bigger, and in this case, you have a smaller circle with a smaller epsilon, right? And what you do here is that when you have more epsilon, when you have a greater epsilon, what does it mean? That means there is the chance that you can have more and more and more members in your neighborhood. If you have more and more and more members in your neighborhood, that means it is highly likely that you are going to be a core. Okay? So you can be a core, and you can, so since you are going to be a core, and maybe a point over here can also help you visit another group. Okay, so you can have very densely connected group of people. So you are going to basically merge them with the help of this greater epsilon, which leads to a kind of tolerance to a number of points that you have to collect. Okay. However, in this case, your neighborhood is small, and you cannot be a core very easily. And that also implies that you cannot expand your cluster that easily. Therefore, the big shape over here that you see is now split into more and more clusters. Okay. So this is what you end up with. And this is also kind of in the same line with the earlier discussion we had. So as you if you keep the number of points at the same value, and if you keep decreasing your epsilon, that means you are making the neighborhood small and small and small, and you are making the chance for a point to be a core is what? Low and low. And at the same time, you cannot really expand your cluster that easily, which kind of leads to, again, several splits in your data set. We can illustrate this concept with this animation, which really I like to show you guys. So let me exit the presentation. Okay, it is coming up, and I would like to illustrate how does epsilon and minimum number of points are affecting your end result. So this is something really fun. I usually show this example, which is really fun to me. And here you can just change the epsilon value. You can increase it, you can, decrease it, or you can just keep the maybe default values. So you may want to see how these are going to affect once you run your algorithm. Okay, so but I would like to just illustrate the fact that if you just run this algorithm, you may end up seeing that actually there are arbitrary shapes. Of course, it's not arbitrary, but the point here I'm making here is that they are not really like a spherical shape. Like we don't have data points in the space that we kinda represent in a circular manner. Here we try to achieve to discover this smiley face by doing a clustering. Okay, so if you run this algorithm, okay, what I expect to see and at the end of the day is that this expansion will grow and grow and grow, and it will just stop. It will basically cover the outer circle here, and then it won't be able to jump to inner regions like this. Okay, and once it cannot jump, it will have to start a new cluster, and it will just try to find a new core to start a new cluster, which will also lead to new clusters for the mouth and for the eye of the smiley face. Okay, let it finish the outer circle, and then let it jump to the inner region. You see, I'm done with this. So it had to jump to inner regions. You see the circles. So we basically try to see which are connected to us, and I can easily jump just because of my neighbors, and my neighbor's neighbor is also a part of my cluster. So it cannot really merge a mouth with the eye. So they are really disconnected from each other. And finally, it ended up finding 4 clusters for me. Okay. If you play with the parameters, here, suppose I want to fix the number of points 4, and let's say you wanna decrease the number. Okay, this is the number of points. Let's say 4, and suppose we wanna decrease the epsilon. Okay. Okay, let's decrease and try to be extreme about it. If you say go, let's see the result. You see, I have more diversity now. It cannot really jump to another region, which makes a split in my outer circle here. So I have more and more clusters, which may not be really meaningful. So choosing the right minimum number of points and the epsilon value, it really matters. So you may have to also deal with the parameter optimization of DB-scan algorithm. That is another discussion, I would say. Okay, so let's get back to our presentation and finalize our discussion. And hopefully next time I'm gonna talk about how we can evaluate our clustering. Okay, let me stop here if I can. I usually struggle with this. Stop recording.